I'm trying to do hybrid and unhybrid.
I'm going to hold up 4 fingers, right? And I'm going to say S, and then I'm going to bring this one down. Then I'm going to say P1, P2, P3. So the answer would be SP3. So what's happening is this is SP3, this is SP3, this is SP3, and this is SP3. And all of those SP3s are overlapping with an S orbital from hydrogen. So the only hybrid ones come from the central atoms. Make sense? No? Yes? Okay, good. All right. So one of the things when you're looking to see if something's aromatic, and we'll get into that in a second, is one of the qualifications is they have to be, sure, let me do it again. I'll pick another molecule in just a second. We'll do this one, and then I'll show you the hybridization again. All right, so if you're looking at a molecule and you're trying to figure out whether or not it's aromatic, they have to be, the ring has to be planar, right? So it has to be planar. So if you're looking at a molecule, like this, what's the first thing that I need to do? I'm going to add the hydrogen that are missing, right? Yes. All right, so I'm going to add the hydrogen. And I do that by looking, each one of these points is a carbon. All right? And they should each have 8 electrons around them. So I'm going to count around each one of those carbons and see if it has 8. And if not, I'm going to add extra electrons by putting hydrogen on there. So this one here has 2, 4, 6. It needs 8. So it's going to be like that. The next one here is going to be the same. It's got 6 around it. So it makes 8. They're all the same in this case. They're not necessarily always the same, but in this case, they're all the same. So now to figure out whether or not it's planar, I'm going to figure out what the VSEPR structure is. That's one way I can do it. The other way I can do it is look at the hybridization. So if it's connected to 3 things, like, so we're looking at what this is connected to. It's connected to this carbon, it's connected to this carbon, and it's connected to this hydrogen. So how many things is it connected to?
1, 3.
3, correct. So the steric number would be 3 because it's 3 atoms bonded to it, plus 0 because there are no lone pairs on that carbon. So steric number is 3. What's the VSEPR structure of something with 3 atoms?
Trigonal planar.
Trigonal planar, correct. And that's what they have to be if it's aromatic. They have to be trigonal planar. They all have to be trigonal planar, every one of them. And in this case, they are all trigonal planar. So that would meet that qualification. Now, if you forgot what the VSEPR structure was for 3 things added to it, you can do hybridization instead. Hybridization is if you have something that's sp2, that is planar. It's trigonal planar. So looking at that, now this is where I'm going to show you the trick again. I'll do it in green. Okay. Do you mean these dots right here, like the one I just turned orange? those are the carbons. So at each one of these corners, those are carbons. And the hydrogens are stuck to the carbons. So now we've calculated the steric number to be 3. So how many fingers do we hold up?
3.
3. 1, 2, 3 fingers, and then this is really bad, Andrew. This is a bad drawing. Okay, but they got 3 fingers up. So what's the first thing they say? S. All right, and I drop this finger down. And then what do I say?
P.
P1, correct. And then what do I say? P2. So my answer is SP2. And that's telling me that it's going to be planar. And if it's SP2, then I know that there's got to be a pure p orbital somewhere, because you have S and P's, right? So to get SP2, you hybridize and make a Frankenstein orbital out of these 3. But you're left with one of them that's still just a p orbital. Correct. If it was steric number 4, it'd be SP3. And if it was 5, it'd be SP3D. What that means to combine them is, instead of having an s orbital, which is spherical, or having a p orbital, which looks like a figure 8, you have more of a kind of rounded figure 8, kind of. So sort of a mixture between the two of them. And that would be a hybrid. Almost like if you had an s orbital and you bred it with a p orbital and they came together, they would look sort of like both of them. Yeah, so if it was 6, it'd be S, P1, P2, P3, D1, D2. So SP3, D2. All right. Another characteristic of being aromatic is that it has to have delocalized. Can I explain how let's start this problem off again? Sure. The problem of the hybridization or the whole problem? The whole thing. Okay. I'll go over the whole thing in 1 second because we're about to go over an aromatic compound. Yeah, it is recorded. So for this one other thing it has to do, that's what we're going over right now. Okay, so it has to be planar to be aromatic. Another thing is it has to have delocalized electrons. And to be delocalized, generally what you're going to see is single, double, single, double. If you see alternating single and double bonds, then you'll see some delocalized electrons. And what that means is, instead of being right here or right here, it sort of becomes like this big cloud that kind of hovers over the whole thing. So this one would count for both of those. Let's clear this because it's kind of hard to read now. All right, so I'm going to put the rules for being aromatic up. One is it has to be planar. So that's trigonal planar, SP2. 2, it has to have delocalized electrons. And so that would be double, single, double in that pattern. And then it also has to fit this rule. 4n plus 2 pi electrons. So that probably sounds a little weird, but this is just going to give you a list of possible numbers of electrons that you can choose from. And n can be any integer starting with 0. So if n is 0, what would 4n plus 2 be? So that would be 2. If n was 1, what would the number of electrons be? It would be 6. If n was 2, what would the number of electrons be? 10, right? So they go up by 4 each time. So if it was 3, it'd be 12 plus 2 is 14. N is any integer. So then what you do, once you've made a little chart like this, then you go back and you look at your compound, and we had this one. And we count how many pi electrons there are. And that's 2, 4, 6. And then we want to look for the number 6 on our chart. And if we find the number 6, then that means that it follows that rule. And so this one would be aromatic. Pi electrons are, if you have a double bond, one will be a sigma bond and one is going to be a pi bond. You have a triple bond, one is sigma and 2 will be pi. 2 per 1 bond. Oh, it's not the number of bonds, but the number of electrons in the pi bond. So it's only wanting to know how many electrons are represented by the double bond piece of that bond. Correct. That is correct. And single bonds are always sigma bonds. That's a good question. All right. Correct. Covalently shared. All right. So there are three more that I kind of want to go over. I'm going to combine 12, 13, 14, and 15 just to kind of be able to get to 16 and possibly 17. Sigma bonds are single. Double has pi and sigma. Absolutely, that is correct. All right. So when we're talking about intermolecular forces, what is that?
Like the ion diploid hydrogen.
So there are intramolecular forces, and then there are Yes, those are the intermolecular forces. Ionic. That's a good question, Summer. Right. That is correct, Josh. Intermolecular forces are between molecules. And Hunter's right, they're holding all of the molecules together. So if you have a glass of water and it's in the liquid state, the intermolecular forces are holding the water together. It's like the glue that holds one water to another water. So it doesn't just kind of float away, right, as individual atoms. Yeah. So the types of intermolecular forces we have are London, hydrogen bonding, dipole, and then ion dipole. So London forces, everything has London forces. And then you have hydrogen bonds. You have to have in your molecule in one of the molecules, you have to have either a hydrogen connected to an oxygen, hydrogen to fluorine, or hydrogen to nitrogen. And if you look at the periodic table, you'll notice those three are right next to each other. So there's fluorine in group 7, oxygen in group 6, and nitrogen in group 5. If you take that, it says NOF, but if you flip it, it says phone. I'm not sure if that will help you remember it or not, but anyway. So that's hydrogen bonding. Dipole-dipole would be one polar molecule attracted to another polar molecule. It can be a different kind of molecule, or it can be two molecules that are the same. Like I could have carbon monoxide attracted to another carbon monoxide. And since they're both polar, then that would be dipole-dipole. Now, so that has to be polar things. An ion dipole has to have an ionic compound dissolved in a dipole, dissolved in a polar thing. For example, if I have water, which is polar, and I put sodium chloride in it, then I have ions floating around in there, and they're attracted to the polar water. And then the sodium will be surrounded by oxygens, the chlorine will be surrounded by hydrogens, and that's ion dipole. So in order of strength, we've got, I'm going to go from weak to strong. So 1 is weak and 4 is strong. London forces are weak. What's next strongest? Hydrogen or dipole? Dipole, correct. And then what's stronger than dipole? Hydrogen and then the ion, right? All right. So it goes London, dipole, dipole, ion dipole. No. London, dipole, hydrogen, ion dipole. Correct. Hydrogen isn't the strongest. It's the strongest if you don't have any ionic compounds in there. But if you have an ionic compound in there and a polar molecule, then that would be strongest. And what makes London forces stronger? Which one of these is stronger? The one on the left or the one on the right? And this just kind of came up with that. The one on the right, because it has more surface area. It's longer, right? And what about this one? If I have, let me switch colors. If I have this one, or I have this one, which one's going to be better? The one on the left or the one on the right? Correct, the second one. This one is better because it's more stackable. So if it's more stackable, there's going to be more surface area touching, allowing for those temporary dipoles to be forming constantly, and there will be more of them forming, so it will be stronger. All right. Now, really quickly, if I have a pot of water and I have it on the stove, this is supposed to be fire down here. I'm just too lazy to, it'll be natural gas fire, so it's blue, so that makes sense. Okay, but anyway, so we've got water, and I want to turn it from a liquid to a gas. I have to break some of those bonds, right? So if I have some liquid in there that has hydrogen bonds and London bonds and dipole, compared to another pot that just has London, which one has the higher boiling point? The first one, because I have to put enough energy into the pot to break the hydrogen bonds, the London bonds, and the dipole. So that's going to take more energy, which means I'm going to have to raise the temp pretty high. But the other one that just has London forces, sometimes it can boil at room temperature. Sometimes it can boil below room temperature. So it would be a lower boiling point for something with fewer bonds. Oh man, only have 3 minutes left. All right, that's okay. And go over this other one really quick. I'm going to skip number 16 and go straight to number 17. Go straight to number 17. And for number 17, it says you have nitrogen isotopes. And one of them is nitrogen 14, one of them is nitrogen 15. The mass of nitrogen 15 is 15.000108. We don't know the mass of this one. This one is 99.63% abundance. And this one is 0.37% abundance. I need to find this number, knowing that the atomic mass is 14.007. All right. Correct. So I'm going to take the percentage right here and convert it to a decimal first. So 1, 2, 1, 2. All right. Now I'm going to multiply this times this plus this times this and set it equal to my average atomic mass. So that would be X times 0.9963 plus 15.000108 times 0.0037 equals 14.007. So if I'm looking for this, I just have to solve for X. I'll try to, I've got a minute or two that I could possibly do that.
14.00.
Abundance, both, I suppose. So how do I find 14.007? So that would be given in the problem. Yeah, it's just the mass of nitrogen. So that's the periodic table. So if I needed to know, instead of needing to know both masses, let's say instead I wanted to know the abundances. So let's say I know this and I know this, but I don't know either of these. And there's a formula I can use to solve for that. I have to use the system of equations. So it would be my mass times X percent plus 15.000108 times Y percent equals 14.007. Now, what else do I know about X and Y? The percentages. There are only two isotopes. When I add all the percents together, what does it equal? 100%, right? Now, if I take 100 and I turn it into a fraction, turn it into decimal form, what's that number become? Become 1. Right. So if I'm looking at the fraction form of X and Y, I know X y equals 1. So now I have my system of equations. I have equation 1 and equation 2. So all I have to do is either solve for x, solve for y in this one. So I could do like y equals 1 minus x. So then where I have y right here, I'm just going to plug in 1 minus x. And when I plug in 1 minus x, then I don't have one variable now. So I solve for x. I've got that. Once I solve for x, I plug it in right here and solve for y. All right. I've got to go because I've got one more to teach. But I'm going to record it and I'll post it on there also. So you'll be able to see both